Section 3.7 is where we're really going to go in depth with some of these interpretations we saw in section 3.6. Now we're finding different things, so the interpretations are going to be different, but it comes all back to the derivative is a rate of change. We even saw that with differentials in the previous section. So what I decided to do was to do one of the biggest problems in the book, and for those of you that pay close attention, you may easily see this on an exam or something like that. It'd be worth a lot of points because there's a lot of parts to it. But what's great about this problem is it essentially hits everything that we could possibly want to know given different types of functions. So this time we're given a little bit different information than some of the other ones if you've taken a look at the examples. We're given the price-demand equation and the cost function. Once again, we're dealing with TVs. But notice x equals 9,000 minus 30p. That's supposed to represent the demand x. X is the number of HD TVs when you have a price set at p dollars. And then if you're doing x TVs, c of x would be the cost in dollars for producing those TVs. So we have two functions representing two different things, and there's lots of stuff we want to do with this. But again, notice we're not given a profit function or a revenue function, so that probably means we're going to have to find those. And that's a skill I want you to have as well. All right, so part A kind of sets us up to be able to find those function values that I was just talking about, those other functions that we might need. So it says, express the price P as a function of the demand X and find the domain of this function. Okay, it's asking us to use this equation here, essentially rewrite it. So it says P as a function of X. It wants you to write where P equals, and then this is stuff with X. So in other words, we have to solve for P. That's all it's saying, but it's using technical language to describe that. So if I subtract 9,000 from both sides, I would have X minus 9,000 equals minus 30p. And then how would I solve for P from here? That's basic algebra. I could multiply by minus 1 over 30 on both sides. So I'd end up with minus x over 30 plus 9,000, negative 9,000 divided by negative 30. It's going to give me positive 300. And I end up with this. This is my function of x. P is now a function of x. So this is the first part. So it's just another way to write my demand equation. Now it says this is the price with this demand. Now it says find the domain. That may seem kind of strange because it's just a linear function, right? The domain should be everything. But remember what we're talking about here. We're talking about price and demand where X is representing TVs and price is representing price in dollars. So there's some numbers that don't make sense. For instance, it wouldn't make sense to have a price of negative dollars. So it'd be fair to say that P should be bigger than or equal to 0. Now, realistically, we'd probably never set the price at 0, but in real life, it would make sense. You know, mathematically, it makes sense. So we would set it up this way. Now, if I solve for this, it'll give me a range value or a range of values that are allowable for X. In other words, it'll give me the domain. So what I've written here is the function greater than or equal to 0, and it gives me an equation to solve. So I'm going to move or an inequality solve. I'm going to move the 300 over, and I have minus x over 30. It's greater than or equal to minus 300. And then multiply by minus 30 on both sides, and I get x. Because it's negative, it's now less than or equal. So x is less than or equal. Minus 30 times minus 300, we get 9,000. Now, can x be anything below 9,000? Well, if x is negative 5, what does that mean? How do you manufacture negative 5 TVs? That doesn't make sense. So I'm going to add to this and say that x should also be bigger than or equal to 0. So the domain is what values of x make sense to plug in, and this would be the domain. These are values of x that would make sense to plug in. Now that function we just found we'll come back to later. I have it written down. We'll bring it back up when we need it. But now we're asked for something that we already have, and that's the marginal cost. Well, we almost already have it, right? You should know automatically marginal cost. This is an easy question. It's just asking for C prime. But notice we have C. So all we got to do is find this derivative. So it's 150,000 plus 30x prime. In other words, our marginal cost is actually constant because the derivative of 150,000 is 0. Derivative of 30x is just the number in front of x, so it's 30. So this is telling me that the cost changes in a uniform way, that no matter what you plug in for x, the change in cost is going to be $30. Now with that, we can come down and we can start talking about revenue. Now revenue, usually what we've been doing is we've been given the revenue function, right? Once we have revenue and cost, we can start talking about profit and all kinds of things, but we aren't given the revenue function in the original problem. But think about what we found in part A. So in part A, I found the following. I found that we could write the demand as minus x over 30 plus 300 equals P. But think about what revenue represents. Revenue is the amount of money you're bringing in. For each TV set, because X is TV sets, for each TV set you sell, R of X represents the total revenue for everything up to that X TV set. Well, how else could I calculate that? Well, what if I was selling a TV set for $100? That'd be pretty silly, right? But if I was selling a TV set for $100 and I sold 5 of them, then the revenue, the money I bring in, would be 5 times 100 or $500. So in other words, whatever the price is, however many I sell or make, if I'm selling them all, that's X. And the price, when I multiply these, it gives me the revenue. But when we rewrote this function, we had another way to write price in terms of X, so we can keep this in terms of X. So this is actually X times minus X over 30 plus 300. In other words, this is minus X squared over 30 plus 300X. So anytime you're not given the revenue function, you can find it by calculating X times P. And if you have a function for P in terms of X, you can convert it over to a function of X, which we'll find very useful. And again, with the cost and the revenue, I can start talking about profit and all that stuff. Now it says state its domain. The domain will be the same as the domain for the demand function. Now I won't say the next 2 problems are easy or the next 2 parts are easy, but compared to what we had to do at the beginning, they kind of are, because you got to have this definition memorized. And as soon as you see marginal, you should think, oh, it's talking about R prime. Now, just a minute ago, we found that R of X was equal to minus X squared over 30 plus 300X. So that means R prime of X is going to be the derivative of this. Now, I'm going to write this a little carefully, and I'm going to say, okay, that could be minus 1 over 30 times the derivative of X squared. Now, X squared, the derivative is 2X. And then plus the derivative of 300X, but that's a number times X, so this is just going to be plus 300. All right, we've seen this before, a very similar function. And so 2 times minus 1 over 30 is minus 1 over 15. X plus 300 is what we're left with from before. So here's the marginal revenue. Now, of course, we want to use that, and that's what part E is asking us to do. It says find R prime of 3000 and interpret it. Now, it also asks you to find like R prime of 4500 or something and interpret it. I'll just do one because the interpretations are basically the same. So first, calculating R prime of 3000. We have R prime up there, so this is just asking us to plug this in for X. So this will be minus 1 over 15 times 3000 plus 300. Using your calculator or thinking about it a little bit, because really this is 3000 divided by minus 15. That's one way to think about it. I get minus 200 plus 300. In other words, I get 100. But certainly, in my class at least, that would not be a final answer. The real work here is the interpretation. We could give R prime to an algebra student and ask them to find R prime of 3000, and they would just plug it in and they'd find it just the same. The calculus part of this is the interpretation. So remember, this is instantaneous rate of change. When X is 3000, we're making 3000 TVs or producing 3000 TVs. One way to say that is we're at a production level of 3,000 TVs. So that's what I'm going to start out with. I'm going to say at a production level of 3,000 TVs, I know it's HD TVs, but I figured that that's implied. So at a production level of 3,000 TVs, right, this is the change in revenue. It's positive and it's 100. So I would say it's increasing. So the revenue is increasing by $100. Now we can be more specific. This is a derivative with respect to x because r is a function of x. X is the number of TVs. So this is the rate of change in revenue with respect to the rate of change in the number of TVs we're making. So in other words, we can say the revenue is increasing by $100 per TV. Notice I didn't say per week or per month. It's per TV because the derivative is with respect to x. Now, if we had revenue with respect to time, then we'd say something else. So this type of interpretation is very important to be able to do, whether it's the revenue function, the profit function, or the cost function. All right, part F seems like a huge question, and it can be if you don't approach it right. What part F wants us to do is analyze a situation, graph the costs and revenue functions, and look at where they match up. That's the break-even point, and figure out where there's loss and profit. Now think about it. Where would there be loss? Well, profit is revenue minus costs. So if revenue's larger than cost, you made a profit, right? If revenue's under cost, then you made a loss. So we want to figure out exactly where these values occur. To do that, we're going to need the graphing calculator. Here I am in our graphing calculator, and what we're going to do is we're going to graph those two functions at it as it asked us and try to figure out those break-even points. The break-even points are interesting because they represent where profit is 0. So what I'm going to do is go into y equals, and as you can see, I've already typed in my functions. If you're not sure how to type in the functions, you press the X button right here under the word link, and I'll type an X for you. Also notice that I put parentheses around the first term for the revenue function. And then finally notice that actually the order here doesn't matter. You could put cost function in first, or you could put in revenue function first like I did. Now once you have those in there, you should go and mess with the window. Now you can tell I was already in here because I'm guessing your window looks a little bit different. What I did was I changed x min, the smallest x we should see, to 0, and the largest x we should see to 9,000, because I figured that that's the domain and that's what we should be looking at. X scale I left alone because x scale is what we're counting by, and I figured the calculator picked something fine. Y min I started at 0. Doesn't make sense to be talking about negative values there either. And then Y max, actually I played around with this a little bit. I started out with 150,000. But if you really look at it, and I'm going to press graph, 150,000 is the y-intercept of our cost function, which is linear. So that means the cost function we won't even see because it's starting at the top of this screen, so that you can see this is pretty useless. You want to be comfortable playing with these numbers. So I go into Window, and I say, you know what, that wasn't enough. Let me try something really big, like 500,000. Press graph. Nothing gets hurt if you're wrong because you can just go back and change it again. Oh, there we go, a nice picture. Now I want to see a little zoomed out from this. So I'm going to go one more time into Window, and I'm going to go up bigger, and maybe I say 650, 750, something like that. I'm going to go really big for 750,000. And really, you just play with these numbers based on what your functions look like. I know revenue is going to be a parabola, and I know cost is going to be a linear function because of the powers on the x. All right, these 2 points where the graphs cross, those represent our break-even points, and to find them, we are going to use the calculate menu. You press second and trace, and then number 5, intersect. Press enter first curve, enter second curve, and then when it says guess, go closer to the point that you're interested in. So we'll start off with this right-hand one. Press enter, and you'll see it guesses, and it finds it 7,500 to 375,000. So you jot that down. We'll mess with that in a little bit. Now it crossed down here too, so I'm going to press second, calculate, and I'm going to say intersect first curve, second curve. This time when I say guess, I'm going to go down towards that point on the left. You want to get pretty close to it, otherwise it might go find the other point we already found. So that's why I'm still clicking. Once your cursor is reasonably close, go ahead and press enter. And we have our other point, 600, 168,000. Now the question is, what do we do with this information and what else can we get from it? All right, so if you were working on this problem, what you would do is you'd sketch this graph real quick. That's kind of hard for me to do with the software I'm using. So what I've done is I've brought a picture from our calculator right here. But when you draw it by hand, you just need the basic shapes. It doesn't have to be perfect. I'm going to go ahead and label our axes. And this right here would be X, because remember that's the number of TVs we're making. And this we could think of as dollars, where it's revenue depending on which function we're looking at, or cost depending on which function we're looking at. Remember, revenue was the parabola and cost was the linear function. All right, and we found the break-even points where revenue and cost equal, and those points were 7,500, 375,000, and 600, 168,000. Right, that's telling me that for X values of 600, production level of 600, revenue and costs are the same, and a production level of 7,500, revenue and costs are the same, meaning there's no profit. Okay, what else can we say? Well, if you remember, profit is revenue minus cost. So if revenue is bigger than cost, you make a profit, right? And here, revenue is clearly bigger than cost, so in here, this is a profit. All in here. That means for these X values, from 600 up to 7,500. So in other words, if X is between 600 and 7,500, we have a profit because revenue is above cost. Notice I didn't put equals on here because when X equals 600, we have a profit of 0. When X equals 7,500, we have a profit of 0 because they're break-even points. Now what about a loss? Well, a loss will occur if cost is bigger because then we have negative profit. And actually out here, notice the cost function is above the revenue function, so this represents a loss. All these X values for when X is bigger than 7,500. Cost gets out of control when you're producing that many, exceeds our revenue, so we lose money. And right here, this little bit right here, you also see the cost is higher than revenue. So in here, we also have a loss. And notice that's when X is less than 600. Now, X can't be smaller than 0, so this would be X between 0 and less than 600. Between 0 and 600, not including the 600, we have a loss. So if you make too few TVs, you're not making enough to overcome the cost. If you want to be able to make a profit, you have to make between 600 and 7,500 TVs. More than 7,500, the cost goes out of control. So all that information came just from these graphs. If you can label a graph like this, then you can analyze a problem very, very deeply. Well, after that part, I guess the last part of this problem seems pretty straightforward, right? We're asked to find the profit function, find the marginal profit, which you know is just a derivative, and then interpret the marginal profit at 1,500 for X. So this all comes right after really analyzing the profit, but we never actually found the profit function. Well, remember the revenue function we found earlier in the problem. Revenue was minus X squared over 30 plus 300X. So profit, I think I've said it enough that you now remember, is revenue minus cost. So profit is going to be minus X squared over 30 plus 300X minus 150,000 plus 30X. So this will be minus X squared over 30. 300X minus 30X will be 270X. And then the negative distributes, so we have minus 150,000. Now the marginal profit is just the derivative of this function, so it's p prime of x. All right, so this will be a minus 2x times 1 over 30. And then plus 270. I'm just taking the derivative as I go. And then 150,000 is a constant, so its derivative is 0. So I end up with minus 1 over 15x plus 270. And so finally, we have to find p prime of 1500, and the more important part, right, interpret it. Well, p prime of 1500 is equal to minus 1 over 15 times 1500 plus 270. Right, if you calculate this, this ends up being minus 100 plus 270, so you get 170. So this tells me that at a production level of 1500, profit is increasing by $170 per TV. Now you'll find that most of the problems that you work through will be similar to this. They won't all be quite as long. This one contained basically everything you could possibly ask. But the other problems, while shorter, will have the same techniques as this. So if you can handle this problem, I think you're pretty well set up for understanding the whole section.